Alright folks, so we are continuing with this section and we are looking for the maxima, minima, and the inflection points of this function f of x. So remember, for the max and mins and the increasing decreasing intervals, you're going to need to find the first derivative, and whereas for the inflection points you need to know the second derivative. So here we go. Let's begin with part 1 of the problem, starting with writing the f of x. The f of x is x cubed minus 3x plus 2. So that's the first function, and then the derivative. The derivative of x cubed is going to be 3x squared. Derivative of 3x is going to be 3. And this is not enough. We still need to factor as much as possible. So 3 is the GCF. We're going to take it out. We get x squared minus 1, which in turn is 3x minus 1, and then x plus 1. So now, what makes the derivative equal to 0? This happens when either the x minus 1 is 0 or when the x plus 1 is equal to 0. And this happens when x is equal to 1. This happens when x is equal to negative 1. So far we have two critical numbers, and notice I ignored the 3 because the 3 itself over here can never be 0. 3 is always going to be 3 no matter what. So now that we have the first derivative, we're going to go ahead and draw the line and consider the first derivative test. So here we go. This is the line, and this represents all the numbers in the world from negative infinity to positive infinity. And we have the negative 1 and positive 1. Those were the critical numbers. Negative 1, positive 1. There we go. So next we have to find a test value from each interval. So remember, this is the first derivative test. So I need a number between negative infinity and negative 1. Let me pick negative 10. And I'm going to pick a number between negative 1 and 1, let's say 0. And I'll pick a number after 1, let's say positive 10. So where do these numbers go? They go into the derivative. So here's the derivative. Pick any of those and plug in negative 10 into it. When you do that, you will notice that the answer will turn out to be a positive value. For 0, when 0 plugs into the first derivative, it ends up giving you a negative value. And for 10, you end up getting a positive value again. So having a first derivative be positive means that the function f of x is increasing. And having a negative that's, a first derivative that's negative means that the function f of x is decreasing and then increasing again. So there you go. So that means what? If we go up, then we go down, then negative 1 has a maximum. And if we go down, then we go up, that means 1 has a minimum. So they had asked us for the places where a relative max or min is found, and we just did it. So we're going to say x equal to negative 1 has a minimum, or has a maximum, and x equal to 1 has a minimum. Okay, so this is the end of part 1. Let's look at part 2 next. Okay, so now that we have the maxes and mins of the function, we are going to turn our attention to part 2 of the problem, which is the inflection points. In order to find the inflection points, I need to pick up the first derivative and differentiate. So here's the first derivative. I'm just going to take the whole thing, grab it, and find the derivative of it. So it doesn't matter which one you pick. We're going to pick it up and drop it here. There we go, paste, and pick up whichever part and you differentiate it. So actually for me, the easiest one to differentiate is going to be the very first thing I wrote over here. So I'm going to start with that and say, what's the derivative? For 3x squared, the derivative will be 6x. For 3, the derivative will be 0, which means I don't have to write it down anymore. So this is just the derivative right there. So this is the second derivative, and again, what makes it equal to 0? So what makes the f double prime equal to 0? This happens when the 6x itself is equal to 0. So this means that x has to be 0, because 0 times 6 will still be 0. So this is my critical number for the second derivative. By the way, I didn't write it down for the first derivative, but we're also supposed to say when is f double prime undefined. So this is undefined when, well, in this particular problem, there's no solution. It's not possible because the derivative does not have a denominator. So the same thing would have happened with the first derivative. I forgot to write it earlier, but that's normally included in there. So at this point, we are ready to make the line, and this represents the second derivative. Again, it has negative infinity, positive infinity, and it has the critical number in the middle. So the critical number in this case was 0. Okay, the 0 because of this. Okay, so test values. We're going to pick a test value before 0 and a test value after 0. Let's pick, I don't know, negative 10, and let's pick positive 10. So we're going to grab those numbers and put them into the second derivative. Okay, so if we put them into the second derivative, negative 10 times 6 will be negative 60 at the end. So this is going to be a negative amount. And when I do the same thing with the 10, 10 times 6 will be basically positive 60. So this is positive, which means that the function is going to have a concavity down, and the function is going to have a concavity up, basically. And because we're going concave up, then concave, or concave down, then concave up, when the concavity changes, we get in the middle what's called an inflection point. So the question said, where are the inflection points? We're going to say x equal to 0 has an inflection point. Okay, sounds good. And the final step here is to sketch the graph of the function f of x. So in order to sketch the graph of f of x, we're going to make the xy plane and just kind of recall that there were interesting things happening at -1 and +1. There was an interesting thing happening at 0. So at 0, there was an inflection point. At -1 and 1, we had a max and a min. And so, you know, using the graphing calculator and just kind of a little bit of a logic, we can pretty much determine that the function was going up from negative infinity to -1. So it's going to be going up this way. And it's going to be going down from -1 to 0. Actually, as a matter of fact, it goes down from -1 to 1. So it's going to look something like this. And then it goes up from 1 to infinity. Now, what about the concavity? Is it going up this way, or is it going up like I did it earlier? According to the second derivative, we're concave down from -1 to, from negative infinity to 0. So that's how the graph is going to look. So far, it kind of looks like this. We are going up until we get to the maximum, and then we're always concave down. And then at 0, the concavity switches. So I don't know if it passes through 0 or it passes through somewhere here. All I have to do is, you know, get the answer to what the x would give us if the function takes on the value 0. So the function was f of x equal to x cubed minus 3x plus 2. If I put in 0 here, I would get 0 cubed minus 3 times 0 plus 2, which at the end is going to be 2. So this tells me that the function is actually not touching 0, 0. It kind of looks more like this. It kind of goes somewhere high where the y-coordinate here is 2, basically. And it's still going to be going down, and at the same time, it's going to switch the concavity. So the concavity is going to be concave up this time. So something maybe along those lines right there. Okay, so let me make it a little bit more smooth. So here we go. Again, I don't really know how much it's going to dip over here at 1. So if you want to find out, we're just going to plug in 1 into the function and get the answer. So when x is 1, we get 1 cubed minus 3 times 1 plus 2, which means it's 1 minus 3 plus 2, which is 0. So that means that it should be touching the x-axis. So, you know, my graph is sort of accurate, but, you know, maybe I should lower it down just a little bit more to touch 0 and come back up like that. So this is what we call the sketch of the graph of f of x, which has the equation x cubed minus 3x plus 2.